Hello! How's it going? Today we're flying through the universe again. Enough of doing small calculations like the ones we did in the previous videos. Today we're diving into the mind of a little astronaut that will navigate planet Formalhaut II in the constellation of Piscis and its little natural satellite, Little Formalhaut II. While the problems in the previous videos may have been a bit tedious, they were necessary stepping stones to get here. But if you've worked through everything I've talked so far, put on your helmet because we are flying to Piscis. Welcome to Binnacle Project.
Binnacle Project.
As always, let's read together a statement. It says, as the astronaut Rocannon approaches the planet Formalhaut II, he observes Little Formalhaut, the natural satellite of Formalhaut II, at an angle of 53.13 degrees relative to the radial direction toward the planet, y-axis. There you can see that they are giving us a little sketch. The total force exerted by these two bodies on Rocannon and his spacecraft is, with a combined mass of 8,000 kilograms, is at that moment, and there you can see that they are giving us the force vector, 9.5 I minus 66.4 J in newtons. Section A says, at what distance r prime is Rocannon from the satellite? Section B says, at what distance r is Rocannon from the planet? And they are giving us as data the mass of the planet, 4 times 10 to the 23 kilograms, and the mass of the satellite, 2 times 10 to the 20 kilograms, and of course the gravitational constant. So now, let's get to it. Well, the first time you read a problem, you panic. It also happens to me. But on a second lecture, on a third lecture, you begin to think on the way to solve it. So the first thing we're going to do is to redraw it in order to make the necessary annotations. Look, it seems that the action happens in the fourth quadrant. So that's why I'm drawing the Cartesian plane this way. This is the x-axis and the y-axis. The action happens here. This is the first quadrant, the second, the third, and the fourth. And they say that here we have our little astronaut. This is Rocannon. Here you have it. And this is the planet Formalhaut. This distance is the first magnitude we are asked to calculate. And on the other hand, they are telling us that at an angle of 53.13 degrees from this axis appears its natural satellite, Little Formalhaut. And we are given the mass of the planet and the mass of the satellite, and also the mass of our astronaut Rocannon and its spacecraft. So now it's time to consider that they are also giving us the total force these two bodies are exerting on our astronaut. Let's say that this is the total force, this is the total force, and they are telling us that this total force is 9.5 on the horizontal direction and negative 66.4 on the vertical direction, of course, in newtons. So, do you know how to proceed? Whenever you face a physics problem, you need to establish a solid starting argument. Then try to mentally map out the mathematical steps you'll take to see if they lead you to the solution. It's a bit like a game of chess. You must imagine a move and mentally simulate the next moves to determine if you are on the right path to win. This exercise requires calm and intuition, but by doing it, you'll be able to rule out unhelpful paths and glimpse the correct one. With that said, let's proceed. We are given the total force these two bodies exert on our astronaut. What do you think about the following? The first thing we're going to do is to calculate the force this planet exerts on our astronaut. Yes, we don't know the distance r, but we are dancing with it. Second step, let's calculate the force only the satellite exerts on our astronaut. And of course, we don't know the distance r prime, but we are dancing with it. Then let's sum both forces in order to have the total force. We will be dancing with r and r prime, no problem at all, because then we will equate that total force with the one they are giving us in the statement. And I'm sure that we will be able to solve for r and r prime. Now, if you want, you can stop the video and try to do it yourself. Don't worry, because I will post the minute of the solution in the comments box. Let's begin. Let's calculate the force exerted by this planet on our astronaut. Force by the planet. By the planet. And you already know how to do it. The first thing we're gonna do is to have a unitary vector from our astronaut towards the planet. This one. This is the vector that we need, a unit vector. Let's say that it is u sub p, unit vector. Unit vector. And can you guess this vector? It's very easy. As we are working on the y direction, this unit vector will be 0, -1. 0, -1. That's it. Step number 2. Now it's time to calculate the force. The force that this planet is exerting on our astronaut. And it's time to call Newton. The force equals, don't forget that all the formulas we need, you can download them from the link I'm leaving in the comments box, okay? There comes the gravitational law. G multiplying creating mass, multiplying test mass or suffering mass, divided by distance squared, okay? This is the force, but in magnitude. No unit vectors necessary or negative signs at all. And we are also using the superposition principle because we are considering that for this calculus, the satellite doesn't exist. We are working only with the planet. Now there comes the third step, where we are calculating the force vector. Let's call it F sub p. And that will be the force that this planet is exerting on our astronaut, but in vectorial form, just by multiplying the force in magnitude, g m divided by the distance squared, multiplying the unit vector 0, -1. And now it's time to abandon the mathematical notation and use the physical notation, the vectorial physical notation. This quantity multiplying 0, 0. And this quantity multiplied by -1 will be negative g m divided by the distance squared. And as this is the second coordinate, the vertical coordinate will be j. Okay? And anything else needed? The units. Please don't forget, never ever forget the units, because this is very, very important. As I run out of space, I will erase the previous calculations, but I've written here the conclusion. This is the vector force, which represents the force that this planet is exerting on our astronaut. This force acts downwards, so that's why we only have negative j component. I won't draw it here because the sketch would be very confusing. Now it's time to calculate the force exerted by the satellite on our astronaut. That is, the force by the satellite. And we are proceeding the same way. First step, let's create a unit vector towards the satellite. This one. This is the unit vector that we need. Let's call it u sub s unit vector. Any idea? In order to clarify the situation, I redraw here our unit vector, u sub s, the same as the one that you can see here. And we are only told that this is a 53.13 degrees angle. And as we are working with a unit vector, its magnitude is of course 1. We want to calculate the length of these two bars because then we will have the coordinates of our unit vector. That is precisely what we need. So let's say that this bar measures A and this bar measures B. As you can see, the length of this bar is the same as the length of this other one, which is precisely the opposite leg of this triangle, the opposite leg of 53.13. Can you remember the definition of the sine of an angle? The sine of our 53.13 degrees is defined as the opposite leg, A, divided by the hypotenuse, 1. And then we can solve it for A and we will have the first coordinate of our unit vector. We can do it together using the calculator. And please have it in degrees, not in radians. The sine of 53.13 equals 0.8. 0.8 is the first coordinate of our unit vector. And on the same way, can you see that this bar is precisely the contiguous leg of our angle? Contiguous leg means using cosine. The cosine of an angle, cosine of 53.13, is defined as the cosine leg, B, divided also by the hypotenuse, 1. So here, doing the cosine of 53.13, which is 0.6, there we have the coordinates of our unit vector. But be careful, because it is necessary to consider that 0.6 is a negative coordinate. That's why the unit vector that we are using will be 0.8 minus 0.6, minus 0.6. You see? Second step, now it's time to calculate the magnitude of the force that this satellite exerts on our astronaut. Don't forget that we are using the superposition principle, which means to forget about the planet and considering that we are working only with the satellite. Having said that, the magnitude of the force will be calculated using Newton. G, multiplying creating mass, M prime, suffering mass, M, divided by the distance squared, R prime, but squares, of course, in newtons. And finally, we are calculating the force vector. The force vector of our satellite. We are only multiplying the magnitude of the vector, G, M prime, M, divided by the distance squared, multiplied by the unit vector, 0.8 minus 0.6. And it's time to abandon the mathematical notation in order to use the physical notation for vectors. We are multiplying G, M prime, M divided by R prime squared, multiplying 0.8, and as this is the first coordinate, the horizontal coordinate, the unity vector will be I. And now we are multiplying the magnitude by negative 0.6, negative G, M prime, M divided by R prime squared, multiplied by 0.6. And as this is the second coordinate, the vertical coordinate, the unit vector will be J. And of course, in newtons. Now it's time to add these two vectors in order to have the total force vector. This one, the total force vector will be horizontal component, only this one, G, M prime, M divided by R prime but squared, multiplying 0.8I. And vertical components, these two ones, negative g m divided by r squared, j, minus g m prime m divided by r prime, also squared, multiplied by 0.6 j. And now it's time to consider that we are equating this horizontal component of the total force with 9.5, that is the total horizontal component in the data we're given. We are doing g multiplying m prime m divided by r prime squared times 0.8 must be equal to 9.5. And then we can solve the distance to the satellite. Be careful when trying to solve for r prime, as it is in the denominator of this fraction. Let's invert both sides of the equation. That is r prime squared divided by these people, g m prime m 0.8 must be equal to 1 divided by 9.5. 1 divided by 9.5. And now it's time to send all these magnitudes to the other side, multiplying, and finally square root. Here you have it. R prime will be gmm g m prime m times 0.8 divided by 9.5 and square root. Now it's time to use your calculator and we will have the distance to the satellite. If you did it correctly, hope you obtained 2.99 times 10 to the 6 meters, approximately 3 times 10 to the 6 meters. And we are also doing the same with the vertical coordinate, that is, we are equating these terms with negative 66.4 j, and we will obtain the distance to the planet.
Binnacle Project.
Let's do it. Negative g m divided by r squared. We are not using the unity vector j anymore, as we are already working on the vertical component. Minus g m prime m divided by r prime squared. This must be multiplied by 0.6. This must be equal to negative 66.4. Negative 66.4. And don't forget that we are trying to solve for r. I consider that it will be very interesting to put all these magnitudes in the calculator. We already know r prime, and it will be better for us to solve. If you did it carefully, hope you obtained negative 7.11. Now we are doing negative g m divided by r squared must be equal to negative 66.4 plus 7.11. And negative 66.4 plus 7.11 equals negative 59.29. And we can remove the negative signs at both sides, and it's time to invert both sides of the equation. R squared divided by g m equals 1 divided by 59.29. This denominator will fly to the right side at the numerator, and finally square root, that is r equals g m divided by 59.29 and square root. We can do it together. 6.67 times 10 to the negative 11, multiplying the mass of the planet, 4 times 10 to the 23, multiplying the mass of our astronaut, 8,000, divided by 59.29, and finally, a square root. We are obtaining 6 times 10 to the 7 meters. And the problem is over. In this problem, we didn't need to introduce any new formulas or procedures. The most important thing that we've done was the setup. Don't forget that we were told the total force of our astronaut. That's why we calculate the total force exerted by these two bodies on our astronaut using r and r prime as variables, and no problem at all. Finally, when we obtained the total force, we equate each one of its components with the given data. And that was it. And now, watch a theory video if you think you've gotten lost in some aspects, or skip to the next exercise to continue climbing. And as always, like, turn on notifications and comment. See you soon!